Yes. Okay, guys, this is, let me stop here. Okay. So let's start, Claudio. No matter if Ismail is not here or not, he could join later, I guess. And let's share screen. Let's go. So this is lecture 16 of our course, and Physics 140, and this is the main review of what we had before, meaning the last class we introduced the Schrödinger equation in one dimension. So this means that we have an expression now to look in the quantum world for something that looks like the Newton equation. We discovered that particles somehow behave as waves when the scale is right, meaning in the case of electrons will be dimensions of the order of angstroms, comparable to the interatomic distances. So the nature of the interactions of particles with potentials in that scale is such that Newton's law is no longer valid, and we have to find an alternative way of of actually describing the physics on this scale, and this is what we have done. We produce an equivalent representation, which is the Schrödinger equation. And this is the Schrödinger equation for a free particle. So we have something that has to do with the kinetic energy, which is this first term here. We recognize features of the kinetic energy on this term. And this second term is a measure of the total energy of the particle. So the total energy of the particle in the case of a free particle energy is equal to the kinetic energy of the particle. So this is the way it works. So this is the one dimension Schrödinger equation for a free particle, okay? And we know that this thing has a solution, and the solution that it has is something like e to the I k dot x minus omega t. So this, we know that this first factor here is the solution to the equation, and also we know that this is a linear equation. So if one if one function is a solution and the second function is a solution, the sum of the two functions is also a solution, and that's what I'm representing here. We have the sum of two things that are solutions. This is a solution for a free particle. It has a definite k and it has an energy that we recognize is equal to h bar omega. Okay, so for this wave function to be a solution to the Schrödinger equation in one dimension of a free electron, it must comply with this equation. Okay, so this is what I'm saying. This is, so if I want this guy to be a solution, I have to put it in here and verify that it is a solution. And what do? Well, I plug it in and make the derivative with respect to time. Here, the derivative with respect to time gives the same value for the equation, except that it lowers the factor of omega of each one of these guys. See, it's I h bar omega, and that's why the h bar is outside here because of the h bar. The I with the minus I here is canceled. So you just get a factor of omega in front of each one of these terms, okay? Can I do this? No, I cannot. So the time derivative of this wave function is exactly that. And now I have to go to the right side of the equation 1, and I have the h squared over 2m, and I have to derive twice with respect to the position. The derivative of twice respect to the position, it means I have to lower an ik and an ik. So I get a ik1 times ik1. The product of those two things give minus k1 squared. And this minus sign cancels the minus sign coming from the derivatives, and I get this expression. So this thing will be a solution to equation 0 if these two things are true, that h omega 1 is equal to h squared k1 squared over 2m, and h omega 2 is equal to h bar squared k2 squared over 2m. Well, you know, this is what I told you before. This is a linear equation. If phi1 and phi2 are solutions, phi1 plus phi2 must be also a solution. Okay, so the only thing I require is that each one of them separately are a solution. And now what I want to do is write this thing up in why I'm doing this. Well, I'm doing this because before, when we examine only one of these things, we discovered that the probability of finding this particle in space is uniform, it's constant. So there's no localization of the position of the particle. If we remember something about the uncertainty principle, if we have a wave that has a delta K, a delta P, a range of values for the momentum, that will mean that it will have a range of value for the position too. Okay. Here I have introduced by hand an additional, I'm sorry, let me put the pointer, I'm pointing with my hand, it doesn't work. Spotlight. Okay. And I want this guy out. Perfect. So we have this addition here of these two factors, and now the fact that I have put in there two different momentum. Remember that h bar k is associated to the momentum of this free particle wave. So I have two momentum. If I have two momentum, it means that I should have a something like a localization of the electron should appear, okay? And that's what I'm trying to get to. And to do that, I have to take this sum and rewrite it, okay? Because essentially what I want to do is take this, if I want to see localization, I have to take this, multiply by the complex conjugate, and see how the function looks in space. If I have regions of space where there is higher probability for the particle can be than others, which is not the case for a free particle with a single momentum, it should be true for a combination of two free particles with different momentum. Okay, in order to comply with the uncertainty principle. So to do that, I do the trick here of rewriting this thing in a way, you know, I factor out something. K1 plus K2 divided by 2 times X, I factor it out this way, okay? So if I do that, I have to rewrite what's in here, okay? Let's look at the product of this factor times this. So I have ik1 over 2 times ik1 over 2, so I get ik1x, which is what I have here. And from this side I have ik2 over x, but here I have minus ik2 over x. So if I sum both by multiplying them, they cancel each other. So in principle, it gives the correct expression here. How about omegas? Well, with the omegas, it happens something of the same sort, because what I did is I pulled back here minus I omega 1 plus omega 2 over 2 times t. And I factor that thing out, and I get this term in the middle. Why do I do this? Because here I have something that is the complex conjugate of this one. Okay, so if this is the complex conjugate of this one, and they are exponentials, it means that I get a cosine function out of that, because it's twice the cosine of the argument here. What I'm just doing here is remembering the Euler relations. The e to the I theta is equal to cosine theta plus I sine theta. Okay, so when I do that, those two things, I can rewrite this same expression as this one here. And now I'm ready to actually square it, because I know if I multiply this guy by the complex conjugate, all this factor that I have here in front will cancel out, because if I multiply e to the I theta times e to the minus I theta, which is the complex conjugate, it will kill this thing, okay, the first time. So the only thing that I will get back is a times a squared times 4 times the cosine of this expression, okay? The cosine square, and I rewrite the cosine square as a function of 1 plus cosine of the angle, okay? Because this is cosine of half the angle, okay? This expression here, I write it like this. My point is, you can go through this, Claudia, you can go through this algebra here, but the main point is how the graph looks, okay? The graph looks, look, it goes to 4 times a square, and then it oscillates following this, this, what is, this is the wave vector. Okay, this is the wave number here. K1 minus K2 is the wave number of the thing. So it has a periodicity in space. Let's for the time being consider that we are evaluating this for t equal to 0. So this is 0, and so it's essentially cosine of K1 minus K2 times x. Okay, and this, what does this do? This fluctuates between, this whole thing in parentheses here fluctuates between 0 and 2, okay? Is that right? Yeah, between 0 and 2. So it will cancel this 2 that I have here. Where this come from? I guess this comes from this, okay. So essentially, phi squared will go from 4a to 0 in each position. But this is for time t equal to 0. If I turn on the time, which is always turned on, but when I turn on in the equation, essentially what this thing is going to start to move in that direction. So what do I get? I get a distribution that has 2 things. The pattern has localization. The localization in space is now, I have a region space where the electron, if it is an electron, the particle that is being described by this is going to be more probable to be found, okay? But that high probability is going to change with time, because this is also a moving thing that is moving in that direction. So the phi square is not stationary. So it is something that actually depends on time. And it does it like a wave. It travels to the right, with this velocity, with a velocity equal to omega divided by the difference in omega divided by the difference in k. Okay, so that's the velocity with which this thing travels to the right side. When it has a minus sign here, it means that the function is moving to positive values of x, okay? So this is what we have to keep in mind. So the pattern that phi square has is like a wave, and it moves with the velocity equals to this to the right hand. So a few features of this probability distribution is that it's not stationary, it changes with time. We know that when we have a solution that it's a single value of energy, meaning let's see that I can write a solution like this. Phi to x t is equal to phi of x times e to the minus e t over h. This is, you know, a way of, why can I write it like this? Because this is the solution to this equation, okay? So I can somehow I have already done that here, because this is minus I h bar omega is this energy here, okay? So I can write omega here as E divided by H. So this is an omega, okay? So if I write it like this equation is a solution to this equation, okay? So if I write it like this, and well, I've done this like here. Let's get this equation, plug it into my Schrödinger equation in one dimension. I take the derivative here, and the derivative with respect to time gives you E at this side, and the derivative with respect to the twice the derivative with respect to position in this side give me the what does it give me here? Well, whatever it gives me twice the derivative with respect to this side. And let me see, did I do that with you last time, or is something? Yes, I did. This is actually the complete Schrödinger equation in one dimension when we include the potential. If we include the potential in this, I don't remember, I don't recall we have done this. Let me see if I've done this. Yes, I've done. So this is the general solution for this equation. For this equation over here, which includes the terms of the potential. This is not a free particle solution, but it's a solution in the presence of a potential V of x, okay? So phi of x and t is now a solution to this, but it has this way, in this way is the time dependence can be written in this way. If it can be written in this way, I can actually separate variables. That's the key point here, because the exponential cancel out everywhere, and I have this second equation here, which is not dependent on time. It's only dependent on x. The expression here that we have is that the right-hand side is equivalent to having an operator, just as the operator of kinetic energy, but is now the operator of total energy, h, times the wave function as a function only of the coordinate in space is equal to the energy times phi of x. This thing over here looks exactly as what I have mentioned to you before. This is the equation we want to solve in general, okay, in quantum mechanics. And this is an eigenvalue problem, because H is an operator, phi is the eigenvector, E is the eigenvalue, and phi is the eigenvector. When I have an expression that looks like an operators times something is equal to a number times the something corresponds to the eigenfunction, E, or the number corresponds to the eigenvalue, and solving this equation essentially means solving the equation of an eigenvalue problem. This is quantum mechanics. quantum mechanics is actually finding eigenvalue problems, eigenvalue solutions for a particular Hamiltonian or H, which is the expression for the total energy of the system. And we're doing this in one dimension, so that's why there's only a single coordinate. When we solve a problem like this, with the potential included, the probability of finding the particle in somewhere in space is equal to phi conjugate times phi. This is what I've done here, phi conjugate times phi. And look what happens. The conjugated part of phi gives the conjugate part of the spatial part. And here, the only thing that I do, I change the sign on the exponential here. I do that. I change the sign of the exponential. The sign of the exponential gets canceled with this factor of phi. So here I have phi conjugate times phi. So the exponential factor that has to do with the time gets canceled in this way. And only I have phi conjugate times phi in terms of position. So this is whenever I find a solution like this is a stationary probability. Why is that? Because it doesn't depend on time. Okay, the time part is removed. And this only happens for stationary states. And what are stationary states? Are states that have a single energy solution for the Hamiltonian. This is a single energy solution. I showed you before that when we have two energies, this is in the case of the free particle, nonetheless, but you have two energies. K1 is H1, H squared, K1 squared divided by twice the mass is equal to the energy of this part, and the energy of this part is equal to K2. When I do this, I get this distribution, and this distribution is something that does depend on time. It's not stationary. It moves like a wave, as I'm showing here. So in the particular case, when I can write the equation like this, the functional dependence of the time I can write like this, which is the same thing we have done in the case of the free particle, but now phi of x is a solution of an equation that has a potential included on it. So when I find a single energy here, we are in the presence of a stationary state. And when we have a stationary state, it means that the probability of finding the particle doesn't depend on time. It's something that is fixed in space, okay? And fixed in time, not fixed in space, fixed in time, okay? So this is the interesting part. And so this is what we want to solve. And today I'm gonna show you how to solve one problem, the simplest problem that we can solve. And by learning that, you will know, an important fraction of the number of problems that can be solved exactly in quantum mechanics, okay? So there are not very many problems that can be solved. This is, when people go solving problems in quantum mechanics, this is what they do. This is try to solve something like this, giving a certain Hamiltonian or expression for the Schrödinger equation in this way that contains the kinetic energy and a potential energy. What makes one problem different from the other is the difference in the potential energy. So each potential energy is a different problem, and there are 4 or 5 problems in quantum mechanics that can be solved like this, and the other ones are variations of these solutions. So by learning what I'm going to teach you today, you will actually be in a pretty good position, meaning you'll know about 20% of quantum mechanics already, all solutions, okay? So this is fun. Okay, so let's consider now, I went back to the to this problem. Okay, I went back to this problem where we had this the sum of two solutions for a free particle for the wave function for a free particle. So here I have the sum. So my wave function here is the sum of two different energies of a free particle. Okay, so this is one with K1, this is the one with K2. And what this thing do is actually generate something that goes like this, and also it travels in space with this velocity here, because this is a moving part. Okay, this keeps moving in that direction. This is slightly different from electromagnetic waves, because electromagnetic waves, no matter what they do, they always travel with the speed of light. Now, no, there's a dispersion that is not the speed of light. It's something different, okay? And what I'm trying to say, instead of adding two, I'm going to add a distribution of them. So so my wave function for the free particle will be a sum of several free particles like this. This is a free particle that moves with energy K and frequency omega to the right in the x direction. Omega and K are related by the Schrödinger equation. Essentially, H squared, K squared divided by 2m is equal to H bar omega, which is the energy, okay? So there's a relationship between K and omega. So when I do this sum, I have to take that into consideration. I cannot factor out this term out of the integral. I have to put it in, because the omega is a function of K. And what I'm doing here, instead of summing two wave functions of free particles, I'm summing an infinite number, and I'm doing a continuous distributions of amplitudes. So this is the amplitude of the wave function. This is the wave function for the free particle. And you know what I'm really aiming at is trying to describe what happens if the nature of this function A of K changes as a function of K. What will happen to the probability distribution? Or first we have to find out what happens with phi, and then we have to what happened with phi modulus of phi squared. Okay, so this is it. So if I have a very narrow function of AK, you can think of this thing is actually centered in a certain value K0, and and it has a certain width. Okay, this function, what it means is the amplitude of each one of the right traveling waves corresponding to different free particles. And what happens is, if I have something like this, you will get, this is a plot of the real part of the wave function. You will get something that contains it's going to be a broad spatial extent. So if I have something with here the uncertainty principle is working again. Remember, K is equivalent to momentum, and X is equivalent to X. So this is momentum. So I have a narrow momentum here. It produces in space, because this is the extension of the wave function in space. It produces a real part of the wave function, which is fairly extended. Okay, so something like this produce a phi square, which is fairly broad in space. So we know that if this thing is a delta function in K, what do we have here? We have a completely flat distribution, meaning the particle, if this is a delta function, the particle could be anywhere. If this is a narrow thing, well, this is going to be wide. If this is a wide thing, this is going to be narrow. So the real part of the wave function, the extent of the wave function is like that. Now, when we think about a particle, the particle is something with a real, even though it is a particle, it has some sort of real presence, because phi squared means the probability of finding the particle in a point in a region of space, which is nice. Meaning we have the, if we look at this object from a far distant apart, we will still think this is a particle. But if we look in detail to the structure inside, we will see the wave. So this is sort of the things that we want to keep in mind when we try to understand about the meaning of the quantum mechanics. Meaning, how do we picture that in our mind so it works? Okay. We somehow have a better understanding, or at least we think we have a better understanding of Newtonian mechanics, meaning because things are sort of, we can see them, we can intuitively think about them. Since we cannot see objects in the quantum world in a familiar way, we have to really develop the intuition by making examples in our mind. Really, we cannot do it by physical objects. Okay, so this is something that is something that bothers, and it makes the interpretation of quantum mechanics rather difficult. Okay, so what would be the next best, the simplest problem that we could solve using this equation? So this is the one-dimensional Schrödinger equation where we have included the potential in there. So we have the potential term, the kinetic energy term, and that's equal to the total energy. And I'm going to try to search for stationary states, meaning I'm going to assume we can get from a particular problem to this situation. And then if I want the full time dependence, I only have to add for each energy, I have to add this particular term to the wave function. So I'm going to show you how it's done in the full picture afterwards. Okay, but for the time being, I wanted to solve this particular equation for a for a particular potential. What potential? The infinite well potential. Okay, what is the infinite well potential? Is something that looks like this. So the potential is essentially zero in a region of space between 0 and L, and it's infinite in all other values of x. Okay, so it looks exactly like this. So we want to solve for the stationary problem. What does it mean, the stationary problem? As what I mentioned to you before, we have taken out this factor here, the e to the minus I e t over h, and we are essentially solving this equation with VDX, the potential that I have just shown you. Okay. So this is the problem, and we want to find a solution for h phi equal to e phi. But we have certain kind of a problem here, because, you know, for these values of x, h is infinite. Okay, so if h is infinite here, the only thing that makes sense in terms of having a finite solution in this case here is that the wave function should be 0 in this place, because otherwise everything is going to be infinite, and I'm not going to be able to solve this problem in any meaningful way. Okay, so the solution that actually makes sense is a solution that comply with the boundary conditions that the wave function is 0 here and 0 here. Because if it's 0 here, It's also 0 here, 0 here. So 0 over all the axes, the wave function, is 0 over all these axes, the wave function. So I already solved the differential equation, at least in some regional space, here and there. And then I have to solve it in this small room here between 0 and L, which is simple because the particles are free to move here in any direction. So the equation here is the one that I have here, minus j squared over 2m is equal to the energy of the particles times phi. Why? Because the potential here inside is 0. Okay. So, but this equation is only valid between phi, between x equals 0 and x equals L. Okay. So I multiply this by this factor and bring it over this side, so I can actually rewrite the whole thing as this: twice the derivative with respect to space of phi plus this factor here, and since the energy is positive, because energy, this is a potential, and so the energy can only make sense if it is above the value 0 here, which is a question, you know, that we will have to address at one point, but it's a bit beyond to actually prove that that is the case, beyond the nature of this course. But believe me, here the energy is positive, so I will have a particle moving freely with energy positive going here, and so what do I have here? I can rewrite this term here as k squared, and I rewrite the equation. And when I look at this equation, I say, well, what the heck? This is just you know, it's a second order. This is an harmonic oscillator in one dimension, at least for the time being, with the variables a little bit changed. Okay, so the actual solution to this equation is simply a linear combinations of sines and cosine, or exponentials, whatever you want to put in there, because exponentials and complex exponentials, it has to be a complex exponential. A complex exponential is equal to a sum of a linear combination of complex exponentials is a sine and a cosine. So I opted for the time being to actually recognize this as the real part of it. So I'm polarizing my solution, and this is what I said. The general solution has this form with I don't know this parameter and I don't know this parameter. This value k is equal to that. Why is that? Because in order for these two things to cancel, you know, when I take the twice the time derivative of sine, I get minus cosine. When I take twice the time, the x derivative of sine, I get minus sine. When I get twice the derivative of cosine, I get minus cosine, and that's why this term here cancels this term there, and this is why this guy is a solution. Yeah. But now we have to add a further restriction, and we have to add the boundary conditions. We know that phi of k at x equals 0, it should be 0. And if that's the case, I can put here x equals 0, 0. And when x equals 0, it means that this is 0, no problem, because the sign of 0 is 0, but this guy is 1. Well, you know, if this guy is 1, so the value of phi at x equals 0 is equal to bk. So this boundary condition implies that bk must be 0. So the cosine is not a solution to this expression. It has to be only the sine, and it's only the sine because the sine has a 0 value here. Okay. If you describe this, you know, if you move the x-axis and you install it, the x-axis in the middle here, you will get sines and cosines. Okay, but the shapes of the actual functions are going to be the same of the solution that I'm finding. Okay, you can do that. You can verify that later. Okay, so there's no cosine solution for the problem presented in this way with the coordinate axis as it is. This is a zero. The zero is where the potential goes to infinity, and the L is where the other point where the potential goes to infinity. So phi of x this is the solution. We also know that phi of x equal L must be zero in order to comply with the thing, doesn't give an infinite value of the wave of h in this side, because it will mean that this side has to be infinite, and everything infinite doesn't I cannot find a solution for that. So one way of finding a solution is that the function is always zero here. And how do we get that? Well, KL must be zero has to be an integer and times 2 pi in this side here, okay? So for that to be the case, K has to be n pi over L, okay? What does it mean? This is K times L has to be simply n pi, because when it is n pi, this thing here is going to be zero and will fulfill the boundary conditions that I have. Note that n is not equal to zero, because if n is equal to zero, k is equal to zero, and phi is equal to zero, so it's a trivial solution that everything is zero, okay? And that is not a solution, okay? Because well, it's the trivial solution, but it's not a solution. That zero energy, zero wave function. There's if the wave function is zero, it means there's no particle there, because phi squared is the probability of finding a particle. Phi square of zero is zero, so there's no particle. Okay, so we are not going to look for that. So all the solutions start with n equal 1 here. Okay, so this is the general form of the kth solution of the wave function in this region. So it's simply that, and this is it's valid between x equals 0 and x equal L, and the wave function is 0 for all other x's. Okay, so this is my solution, okay, to the problem. So we can see here how they look. So when we start to change the value of n, okay. So the first one is simply a half sign between here and here. So this is the function so when x is equal to L, the argument of the sine function only changes in pi, okay? And the next value, the angle of changes in 2 pi, and the next in 3 pi, and so on. So this is the way the actual solution looks. They should be 0. They are displaced up just for clarity only, and the solution is 0 at the position x equals 0, and it's 0 at x equal L, okay? And the energy, the expression for the energy, remember how we define the energy? The energy is equal to that. It's h squared, k squared divided by 2m is the energy, okay? So this is h squared divided by 2m times k squared, but k squared is equal to n pi over L. So I replace that here, and I see a succession of energy values going up. So this is the E1, which is called the ground state of this solution, is the lowest energy state for a particle to exist inside a confined barrier. So this is a compelling aspect, actually. The minimum energy, it's not 0, meaning it has there has to be some combination of things here going on in order to produce this minimum energy. So you cannot have something with 0 energy located inside the well. This is very relevant because it means that localization in space induces the particle to have some certain momentum. Actually, this particular thing here, this wave function is a sign. A sign is a linear combination of two momenta, of two value of k, one going to the right and one going to the left, that when added up, they provide something like this, that it has an average value of the momentum equal to 0. Everything here has an average value of the momentum equal to 0, because otherwise they will be displacing. We have to remember that the probability distribution of these things are stationary. I can actually square this thing and it will look like, you know, like a bump in the middle and nothing else. And these guys will have nodes, and those won't change with time. Okay, they will be fixed in time. Okay, this is part of it. So, and look what happens to the energy. The energy here is 1, 4, 9, 16. So actually, if this is potential energy, so you can think of this as energy. So this axis, you can think of energy. So this is widely separated from here to here. There's a wide distance from here. This is 16, so the distance is 5. No, 6, and here is 5, and here is 3, and the next one is 25. Okay, so it's going to be 9. So the distance is making between the different energy levels possible for the particles to have while living inside this confined environment is actually increasing. Okay. Now there's a different thing that we need to do is we know that the probability of a particle to be between here and here must be 1, because if a particle lives in this state and I integrate the total probability of finding the part in this region of space, that must be 1. Okay, so it means that the integral between 0 and L of phi conjugate times phi dx is missing here. This should be 1. Or it's not missing, it's understood. Much better. Okay, so if I replace my solution, that's ak times sine square of blah blah times dx. This is the nth solution that we just found. This is this solution that we just found. I square that and integrate overall over this region. That should be 1. Well, this thing over here, I can use the cosine of half the angle, okay, and rewrite it like this. And so I will get something that is a constant value for sine square. Yeah, is sort of the mean value, and something that fluctuates with y. And am I integrating between 0 and x? So essentially, this term over here, the fluctuating term, which I'm integrating over a complete period of 2n y, and this is cosine y. This is going to be 0. Okay, so the only thing that I recover from doing this integral, because it's the factor of 1/2. Okay, it's 1/2 times dx gives L over 2, and since this thing is 0, the AK, the value of AK, in order for this thing to be actually normalized to 1, is I have to sort of normalize the amplitude, so it gives finally the fact that phi conjugate times phi is 1, and this doesn't come out of the algebra, is given by this expression. So A, I can assume freely that it is the square root of 2 divided by L. If I do that and I plug it back in here, phi, it will give me 1. Okay, that's what I know. So every one of these wave functions is properly normalized. meaning that if I take phi 4 conjugate times phi 4 integrated between 0 and L, that will give me 1. Okay. Okay. Wow, I've been very slow today. Okay. So let me, with this in mind, I go back to the general solution. Okay, so the general solution, the complete solution as a function of time for this problem can be written like that. Is phi xt, it is an amplitude. These coefficients here, we don't know. These coefficients actually depend on the initial conditions of the system. This one here is, then what I'm saying is the general solution is equal to the solution of each energy state added by an amplitude. The only solutions that can be possible here are additions of these energy states. So any solution that is possible here should be a linear combination of the solutions that I'm showing you here. And that's what I'm writing here. A linear combination of this solution. And what happened with the time dependence? The time dependence is right back in here. So this is the way the thing depends on time. Note there's an arrow here to this indicate that this h is not square, because this is E divided by h in order for this thing to be an omega. And h squared pi squared over 2ml squared n squared, that's the energy. So divided by h is omega. So this is the omega now. Okay. So everything is legal. The ANs here, because I can sum from n equal 1 to infinity, because I have a complete staircase of states until infinity that can be sort of representing my system. And any state of the system can be written as a linear combination of those states. There's no solution, and let me stress that. Oops. Okay. There's no solution with an energy, like let's say here. It is not possible. Whenever you find a solution to this problem, it has to be in one of these energy states. You can have the system living in linear combinations of these states to begin with, but whenever you measure this thing, they have to be in any one of these states and no others. You cannot find an energy like so, or anywhere that is not one of the points that we're making here. That's why this thing is actually called quantum mechanics. You quantize the energy scale. You cannot get solutions everywhere. Okay, energy is not the only thing that is quantum in quantum mechanics, by the way, but that is something to be said. So if the system is in any one of these eigenstates, let's say a sub n here in this summation is equal to delta Kronecker. So it's only different from 0 when n is equal to m. The probability distribution is stationary, even though phi of xt is a function of time. Yeah, because if I only have one, I have already shown to you that if we have only one energy here in the exponent, when I conjugate that and I multiply by the complex conjugate, those terms cancels out. So this is no big deal. But whenever you have a combination here, this energy, the probability distribution, when you have a combination of stationary states, the probability distribution is not going to be stationary. Okay. Yeah. Well, here I said if two ANs are different from zero, it means I have two energies here. The probability distribution is no longer stationary because you have these cross terms here, okay? Okay, and so, and this is sort of, I was less optimistic when I wrote this, this line here. It says, this is the way we solve most of the quantum mechanical problems. We have a potential, we solve the equation, we find out what the boundary conditions are, and then we look at the solutions, and the general form, we find this set of eigenfunctions, okay, and we find this set of eigenenergies, and write a general solution as a set of unknown coefficients times the eigenfunctions, and we sum all the possible values here, but with all the corresponding energies. So this is the actual way to solve any quantum mechanical problem. Okay, and by learning this, I said here, you solve always 1/10 of the actual problem you can solve algebraically. No, that's not true. This is 1/5. You know, you're very far ahead now, guys. Okay. Yeah. So let's go to a slightly different problem. This is a mathematically a more cumbersome problem, but you know, in terms of conceptually, it's almost the same to what we have been doing, and. So let me try my best to get through this. What I want to solve now is the problem of bound states in a square world potential. So instead of having something that goes to infinity, I have something that goes to a certain value U0. Okay, and you can imagine what will happen. Okay, if the energy is below a certain value here, meaning it's above zero and below U0, you will have an oscillatory solution in this position, and probably the next one will be an oscillatory solution like here, and the next one an oscillatory solution by there, and the next one will go all the way through. It's not going to be a bound state. A bound state is called a state that is actually restricted by the potential to remain with a meaningful probability only in a region of space where the potential is provide rooms for that. Okay. Here, if the energy is this high, meaning remember this is an energy scale, because this is the potential that I'm drawing here. Okay. And so in an energy scale, if I have something that has a total energy that goes like so, this value of total energy, it means that we will fly on top of this potential very easily. Here, it will fly with a different frequency, and then we'll keep flying that direction. That is exactly what will happen. Okay, so let's try to tackle the general features of this problem. First, between 0 and L, the potential is 0, so we are facing with the free particles solution just as we did before. And the difference is that now the boundary conditions here cannot be that the function is equal to 0 at this point. Why not? Because this is not infinite. So you know, the only thing that I can say about the solution in this point, it should be the same as the solution in this side, and also the derivative should be continuous and the wave function should be continuous. That's what I can tell. So at this point, the restriction will be the continuity of the wave functions in order for this thing to make sense, because it has twice the derivative of the wave function. So at least the first derivative must exist and be continuous here. in order to be able to define a second derivative. Okay, so this is the trick. So we have to use the continuity of the wave equation to derive and the derivative instead to find what are the conditions. So for x less than 0 or for x greater than L, the actual wave equation looks like this. Okay, what is this? This is the kinetic energy term. This is the potential energy, which is a constant, U naught, times E times phi. So this is the form of the wave function in this direction. What is the solution for this? Okay, we know that E is less than U naught. So this term here, U naught minus E, is positive. Okay, so I multiply by this factor, and I call this thing here, I call this term K squared. Kappa squared, I'm sorry. Kappa squared, no, K was the other one. K is this one. This is K squared, and this one is kappa squared, okay? Different values, okay? And this value here is essentially positive for energies E less than U naught, okay? So that's why I can, for this energy range, I can write it like that. So if this is kappa squared, this equation here is the solution for an expression like this. So phi of x is equal to c to e to the minus kx plus d times e to the minus kx. Okay. So why? Well, you know, because you can plug in this equation there and find it's a solution. You make twice the derivative of this function with respect to x, and you get a k squared in front of each one of these guys. And since the sign is changed here with respect to phi, you get chi squared times phi from this here. From the first term, you get chi squared times phi, and since this is the sign is changed, this is a solution. Perfect. So we have regions of space here, though. We have a region of space x less than 0 and x greater than 0. Okay. So we need, for the wave function to make sense in any, remember that the square of the wave function is the probability of finding the particle, and we cannot deal with things going to infinity at infinity, in meaning the particle will be most probably be at infinity than in where my solution is. Makes no sense, make no sensible solution for that. So the boundary conditions for these things that are imposed is that the wave function should be 0 at infinity here for this kind of potential, which makes sense. So it means that the actual solution for this region should be c times e to the kappa x. And since here x is positive and we want it to be 0, this is perfect. This should be d times e to the minus kappa x. Okay, so the actual wave function will decay in that direction, and it will decay in that direction. And here in the middle will be this oscillatory thing. Why it would be an oscillatory thing? Because we have this equation that we know it's a cosine by b sine, you know. So here it's oscillatory because there's kinetic energy, and here it's only decays. This is really surprising when we compare this with quantum mechanics. Well, the conditions are the following. The conditions here is the wave function should be, and the derivative should be continuous at this point. That's it. The remarkable aspect of this solution is that the actual wave function penetrates the region classically forbidden. Because if the potential energy is a wall here, in classical terms, this cannot penetrate inside. Okay, it can only get to there, and it should be 0. The concept is this should be the same as the infinite wall. That's what classical mechanics tell you. There's no probability of you crossing beyond a certain point if you don't have the energy to be there. This is not the case in quantum mechanics. There's a slight probability of penetrating an impenetrable wall. Okay. What I've written here are the conditions for the continuity condition. I'm not gonna ask you to do this. This is a rather complicated thing to do, to actually find out that. But doing this, what you do is actually find out what are the solutions to this problem. And this is how it works. And here I have a model for this thing. And here I have I have a potential well, which is as deep as 6 times the energy of the ground state of the infinite one-dimensional well. Okay, this is what they say. What is the energy of the infinite? Let's say the energy, the potential energy goes to infinity. If the potential energy goes to infinity, the ground state energy of the potential energy will be here. Okay, that's what this diagram we should understand this diagram. And this value here of the potential for this particular finite potential well is 6 times this value. Okay. When you do that and you match the boundary conditions at these points for the wave functions, you discover that this particular well can only hold 3 bound states: the ground state and 2 excited states. Afterwards, you go to a continuum state, the one that could travel all over the place without being bound to be staying in this region of space. Okay. We have depicted here, and you can see that this looks very much like the infinite potential well, because the infinite potential well will sort of get here from here to there, and this is the first one. The second one has one intersection in the middle, the same as in the case of the infinite potential well. The next state has 2 intersections in the middle here. So this is the next excited state, but the main difference is that these guys penetrate inside the region what is forbidden for them. This is the region that is forbidden for them. Okay, so and we can get this in a finite potential well. If the well is taller, well, we can get more states, 5, 6 states, whatever. Okay, and we have to find out how many can we get. It really depends on how deep it is. And you can see that the actual energy value, it's a bit lower. So if you have a finite state, the energy of the state is a bit lower. And the fact that the energy state is a bit lower is simply because the wave function is a bit more extended here. So the lambda is longer, and a longer lambda means a smaller wavelength, a smaller energy. Longer wavelength means smaller energy, and that's why this state has less energy than the one in the infinite potential well. Okay, it will be worthwhile taking a look at this. This is how the actual probability function looks for this particular example, and you can see that in all cases there is penetration, but the penetration is higher when the states are getting closer to the continuum. The continuum is the energy range where the particles can travel without any impediment. They are not bound to be located in this well. Okay, so the complete solution of these problems is these 3 energy levels plus the continuum states that travel on top. And so any solution that you would like to consider for this particular system must have a linear combination of all the states that are a solution with the proper energy term associated with them. Here, this is a continuum distribution, as the one that I showed you before, that could give rise to a wave packet, meaning you can have an A of K, a continuous distribution, because every value of K is possible for an infinite distribution like this. Here, you only have confined states, okay? And this confined state have this probability distribution that actually penetrate in the region of in the classically forbidden zone of the potential. Yeah, I'm going to leave this for next time because we are already on time for this lecture. And guys, you have to read. This is the most exciting part of the course. Okay, this is the thing that makes you think in a different way. That everything that you thought it was well, clear and understood somehow gets a bit philosophical. Okay, which is not. The quantum mechanics has a high capability of predicting actual numbers that you can measure. So you really have to try this as understand this as a real reasonable theory to do that. Okay. So guys, this is it for the weekend. I hope you enjoy your weekend too, and I will be sending you now I have already graded your exams. My TA has not produced me grades for you guys yet from the homework, but at least I have the exam, so I'm going to be sending you the solution of the exam and your exams to use for you to check and tell me if everything is all right. Okay. So this is it, guys, for today. I'm sorry that I was a bit, further in time here. Okay. No questions? Good.
Take care, teacher.
Okay. See you guys on Tuesday. Bye-bye.